Welcome to Catch, Finding Celestial Objects with Google's Spatial Indexing Library S2. I'm Daniel Darg at the University of Maryland. What is Catch? Catch, at its core, is a library created by Mike Kelly at the University of Maryland. Since this is a conference on software, I'm going to focus on what I think is the most interesting part of it from the software perspective, the S2 library. You can find the code on GitHub. And Catch is also implemented as a web API with user interface by myself. And you can find that interface at this address. What does Catch do? The main thing Catch does is pre-covery, that is discovering objects retrospectively. So to understand that, I'm going to give a schematic here. In case you're not familiar with astronomical terms, maybe you're just here for the software interest. When we look at the sky, we can put polar coordinates across the sky, right ascension and declination, and we can use these coordinates for 1- and 2-dimensional geometries. For example, when you take a picture of the sky, it's typically a square or a rectangle, and you can characterize such a geometry with the coordinates of, for example, its corners in a database. And whenever you take a picture, it's typically at one moment in time, and you associate that with an astronomical FITS file. If you have one or multiple surveys, then you end up with lots of such images across the sky. These different colors represent different surveys. And something that interests researchers is being able to find pictures of comets and asteroids within such images. So let's say that you're interested in finding the comet 65P within some of these surveys. You go to a database and you look up its orbital elements. These are numbers that characterize the Keplerian orbits of comets. And you plug these numbers into an astronomical library function. And you can compute at any given time where you would find it in the sky, what its RA and DEC would be. So you can see in principle how you might find any such object within an image. You simply compute where the comet would have been in the past at a bunch of different times, and then you compare these coordinates, the RA and DEC, and that time, and you check to see whether those coordinates for the comet at that time would have landed within the boundaries of a telescopic image. So you could imagine iterating over each and every such geometry within all the surveys that you might have and comparing these coordinates. But of course, that is very inefficient because we have a lot of images of the sky. So this is the sky coverage of Catch from its first 3 surveys that were included in its database. And you can see that these covered most of the sky. And in fact, we've added some more recently. So now the sky coverage is pretty much complete. And in the Catch database, you have over 21 million such observations dating all the way back to 1996. So to be able to search through and find pre-covery images for any given comet or asteroid is going to take some special spatial indexing, since you obviously can't iterate over 21 million geometries at a time. So on to indexing and some history. When Mike Kelly first created Catch, he used a simple SQLite3 database which has R-tree spatial indexing. That proved okay, but he made the decision to upgrade to Postgres in order to be able to handle multiple queries at once. Postgres has its own geospatial indexing. However, Mike was disappointed with the performance, so he did what we all do, which is to Google how to make things faster, and he discovered the S2 geometry library. So what is S2? Well, S2 just is a C++ library. So you install it on your machine, and then you have access to various functions and data structures that allow you to perform clever spatial indexing things. So what does S2 do? You can think of the S2 library as essentially doing 2 things. First, The S2 library defines a framework for decomposing the unit sphere into a hierarchy of cells. Each cell is a quadrilateral bounded by 4 geodesics. So each cell is broken down from about 6 cells that cover the whole Earth down to cells that are about 1 centimeter in size, and each of these cells is given a base 64 ID. The second thing the S2 library does is it threads a space-filling Hilbert curve through each and every cell, and the library uses these constructs to make the following operations very fast. So given a coordinate on the Earth, it will quickly find the IDs of the cells that contain that point. So let's apply these S2 concepts to the challenge of precovery. If you have an image on the sky characterized by the coordinates of 4 corners plus a time, then you can input that geometry into the S2 library, and S2 will choose cells to represent that object. So you put in these coordinates and you get out a set of cell IDs, and then you can save those cell IDs to a database. So for this image, we now have the original coordinates, the time at which it was taken, and we have these S2 cells that cover where it is in the sky. Now, when we want to analyze an object like 65P, a comet, we can use its orbital elements to compute the RA and DEC coordinates at different moments in time in the past. And then we can run the S2 library on the fly to figure out what sort of cells would cover that coordinate. And now the problem reduces to the question as to whether the cells that characterize the location of an image are the same cells that characterize the coordinate of a comet at a moment in the past. So here we have the coordinates of a comet in the past computed on the fly. That, in other words, when someone puts in a request to find, for example, the comet 65P, the Catch library will compute the S2 cells that comet was in. And then the challenge becomes comparing whether any of these cells that characterize the coordinate of the comet in the past overlap with cells associated with files in the Catch database. So this is tricky because remember, we've got 21 million entries in this database, and we have an arbitrary collection of cells here, and in any given row we have an arbitrary collection of cells. So how do you efficiently match whether any of the cells in this set can be found on any of the rows in this database? Well, you do that with inverted indexing. This is something that DBs will do for you. So we use a Postgres database, and when you request that Postgres generate an inverted index, it will basically take each of these cells and give each of those cells its own row in an indexing table, and then every ID that has one of those cells gets listed in another column. So if you now iterate through this set and look up the row on which C1- is found, you will be able to find the IDs, that is, the rows on which a corresponding image can be found. And from there, I think you can get a sense of how it is with a little more geometrical reasoning. We can efficiently find intersections of comets and observations from surveys. So here are some diagrams generated by Mike Kelly showing this process in action. So here we have RA and DEC space, and this is a trajectory of 65P in the past. And if we zoom in on this region, we will find an area in which observations have been made. Here's a zoom in. And if you zoom in enough, here is a depiction of the cutout from the FITS file, and you can see that this object was found exactly there, and I'm impressed to this day by the exactitude of it all. And here Mike generated a really fantastic three-dimensional depiction of what I just described. Here is the comet going through array, deck, and time, space, and you can see here are the images taken by the telescope at different moments in time, and this is where the intersection was found. So I encourage you to check it out yourself. This is the Catch interface. You can type in any object into the search field and hit search, and it will generate results that look like this. So this is 65p. This is a cutout from the FITS file showing the comet, and we provide lots of metadata, and we welcome any feedback from the community. We have planned future developments, including breaking Catch down into microservices, which is a process that's already begun. We will streamline in many ways. For example, we're going to discontinue getting our coordinates calculated on the fly from the JPL API. Rather, we're going to compute those locally using the new assist library, and the front end will have a 3D solar system viewer so that you can see a 3D representation of Catch in action. And as for features for researchers, we are going to implement stacking of FITS files so that you get improved photometric data. And we also plan to set up automatic searches for new near-Earth objects that are submitted to the Minor Planet Center. In summary, what is Catch? Catch is an acronym that stands for the Comet Asteroid Telescopic Catalog, and we needed a word that began with H in order to make it Catch, and we couldn't decide on whether it's Hub, Harvester, Hunter, or Hoarder, so we'll go with Hub for now. So that is Catch, and thank you for listening.